Okay, we're going to go ahead and get started. So welcome to Unlocking Full Blade Liquid Cooling, what comes after CPUs and GPUs. Before we get started, there's just a few housekeeping things that I'd like to go over. First of all, everyone here is on mute. We are recording this, and so I'll be sending out the recording to everyone after the webinar, and we're going to be having some live Q&A at the end. So if you are thinking of questions throughout the webinar, go ahead and pop them in that little Q&A box at the bottom of your screen. With that, I'd like to introduce our presenter, Dr. Bill Flaherty. He's our VP of Technology Development here at Alloy Enterprises. Bill brings over 15 years of experience building hardware and leading teams at the intersection of physics and engineering. He's got a PhD from the University of Illinois, and he focused on advanced fluid dynamics and heat transfer designs for hypersonic vehicles. And with that, I'm really excited to let him take over and get started. So here we go.
Okay, thank you, Sam, for that introduction, and excited to be talking to everybody today about peripheral cooling because I think it's a really fascinating topic that's going to become absolutely mission critical for these high-powered AI factory deployments that are coming over the next few years. But before I dive into that, let me introduce who we are at Alloy, really. So our mission at Alloy is to deliver the most advanced cooling solutions with unmatched performance, efficiency, and reliability, right? And so that is our primary focus, is building these components that can cool the most challenging devices that are out there on the market. We're a 5-year-old startup located in Burlington, Massachusetts. It's about 15 miles north of Boston. All of our manufacturing is in the US, and we're a group of mostly engineers, 50 people, 75% of whom are engineers. And we started off by building this cost-effective and scalable manufacturing process that we call stack forging. If you're interested in more details on stack forging, we have an awesome white paper out there that you can read. You can also go and view some of our previous webinars that talk about stack forging, but that's not what we're here to talk about today, so I'm not going to get too deep into that. The way that we work with our clients is kind of as a full stack partner, right? So we're not just a contract manufacturer. We are from clean sheet to delivered component, a partner with our customers all the way through the process. And so we have a library of microgeometries that are only manufacturable with stack forging that we can call on. And then we have a full digital manufacturing suite that allows us to easily pull these geometries that we've already designed into new shapes and form factors in order to meet the specific needs of the customers that we're working with. And that's actually really important for the discussion we're having today on peripherals, right? Because we can take these microgeometries that provide really efficient cooling and put them into components that are made to cool a whole slew of different devices that might need to be shaped differently, that might have really specific geometric requirements. We can really easily do that by combining this library with our digital manufacturing suite. And then this is all coupled, like I said, with our stack forging process, which is really designed from the ground up for scale and for mass manufacturing, right? So there's no prototype machines at Alloy. Everything that we build is built on our production floor. We practice how we play, so to speak. And so we really start from the beginning of a project, focused on how we are going to make this thing in production. But that's not what we're here to talk about today. We're here to talk about peripherals and peripheral cooling. We started off like many other folks did, though, cooling CPUs and GPUs, right? And if you can forgive the pun, that was the hot thing, and still is the hot thing on the market. And so we have a full suite of solutions that we have now developed and deployed out to customers. We've shown that we have, industry-leading performance on these form factors. And yeah, so you can see some examples here. We have a MI355 cold plate for the AMD GPU, a Blackwell cold plate in the upper right-hand corner for NVIDIA GPUs, and some examples of cooling for EPYC processors here at the bottom. These are just a small subsection of the total designs we have, but when we started doing this work, we started in the CPUs, GPUs. We found a lot of interest and traction there, but then we also found folks talking to us about peripherals, right? And their challenges and their needs to cool peripherals. Now, You might be asking yourself, why are we even talking about this, right? Like, if you're familiar with computer architecture, you're probably familiar with things like memory sticks and SSDs. And you think, well, these are low power devices, right? They're fairly easy to cool with air. Why are we even worried about cooling with liquid these peripheral components? Well, first, right off the bat, Kyber is coming, right? So NVIDIA announced the Kyber rack, I believe, just about a year ago now. This will be the rack system that supports the Vera Rubin CPU GPU pair, the kind of next generation system. And they're projecting that this is going to have 600 kilowatts of heat in a single rack. 600 kilowatts. That is massive, right? It's well beyond where we are today, where leading edge racks that are deploying today are pushing 120 kilowatts. And so when you break that down, right, that's 600 kilowatts total power per rack, and you use kind of industry standard ratios, right? So typically what you'll say is if you're cooling just the CPUs and GPUs in a system, you're probably capturing about 80% of the total heat load in the liquid loop, right? And then the rest would need to be cooled by air. So today, in a system where you might be at, 120-ish kilowatts, if you're only cooling 80% of that, that remaining 20% is doable with air, right? And we've seen air systems typically tap out somewhere around 40 kilowatts of total heat load. But now, if we move to these next generation systems, right, 600 kilowatts per rack, you do the math, what's 80% of that, and you take that off the top, you're still left with 120 kilowatts of heat that you need to remove from the system, right? That is as big as the biggest racks we are deploying today. And those racks that we're deploying today already use liquid cooling, right? And it's well above what you can reasonably cool with air at, say 40 kilowatts. And so there's basically no choice. There is going to be a requirement to put more of the heat load into the liquid cooling loop as we move to these very, very high power racks. That's coupled with the fact that it's not just GPUs that are progressing and that are pushing performance envelopes, right? To meet the demands of these GPUs, all of the components in the system are kind of riding this wave of tech development to improve their performance so that they aren't the bottleneck in the system anymore, right? And so things like DIMM sticks, right? So we're seeing the push towards MRDIMM expected to crest 40 watts per stick. I've also had talks with folks talking about DDR6 memory pushing even higher power than that, right? And that's compared to today where you're at maybe 12 to 14 watts per stick, right? So we're talking 4 or 5x increase in power per stick. And then not only that, you want to push those closer together, right? We want to increase the density of the rack. We want to get more memory in there. That means we have higher heat loads packed closer together. All of a sudden, this memory stack up that was, not a problem a year ago becomes a critical system heat driver that you have to deal with. Similar with input output, right? QSFPs, OSFPs. We're seeing estimates of next gen systems that have 50 watts per plug compared to, a fifth of that today. And so again, a huge heat load issue there. Those are oftentimes in, industry standard cages as well. So you have a limited amount of space that you can even put a liquid cooling solution into. And then a final example is solid state drives, right? Like storage. So, an E1.S drive today, very low power, oftentimes not challenging to cool. These E3.S, right? These cutting edge drives that are giving us, better read write speeds, things like that, up to 70 watts per drive. Right? And so across the board, we're just seeing these peripherals go up and up and up and up in performance, and that is pushing their power consumption up higher as well. And then combine that with the fact that we're cramming more and more of them into the blade, and this problem is just huge, right? And so it just can't be ignored anymore. It's not about just cooling the CPUs, GPUs. It's about cooling the entire system. So I wanted to show a couple of examples of components that Alloy is working on to address these issues, right? And because a lot of the what I'll call traditional ways of doing cooling for these components is just not sufficient anymore, right? So when we look at, say, DIMM, The traditional way of cooling it might be to just have cooled end manifolds with conductive paths of like copper sheets that go between them. Maybe if you're pushing up, to a slightly more performance system, you might have a crushed copper tube that's placed in between these sticks. But those systems have fundamental performance limitations, right? So you can imagine with conduction, eventually the thermal resistance gets high enough that you just can't pull enough heat out of the sticks. The crushed copper tubes have challenges getting down to really fine dim pitches as well. They're not very pressure resistant, right? Because you've already yielded that tube to squish it into the form factor that you want. And so with stack forging, we can take a fundamentally different approach, right? And so what you see here is actually a single monolithic part. There's no soldering at all in this, right? So again, if you were to make this out of, say, crushed tubes, there would be, 16 individual solder connections for each of those tubes to connect to the manifold. And each of those is a failure point. We've taken that completely out of the equation here, right? This is a single monolithic piece of metal where everything is connected as it comes out of the machine. And so we've basically eliminated all of those potentials for leaks. Additionally, this is a double-sided cooling structure, and that's how we're going to be able to enable these next generation high power DIMMs is by pulling power out of both sides, pulling heat out of both sides rather, you're able to push the amount of heat that you can pull out up much higher. But to do that, you have to have some really clever tricks for how you design the part, and that's what we've done here. Additionally, especially with memory, we want to be able to upgrade in the field. We want to be able to replace sticks that fail in the field. And so this is designed for tool access so it can enable removal, reinsertion in service. And this particular design is already in simulation. We're showing that we can cool that 40 watts per DIMM to meet kind of what we're projecting the next generation JEDEC specs to lay out for MR DIMM. And then this is all coupled at the end with a bypass, right? And so because we can build complex flow structures into this piece, we can put in a bypass to allow you to tune performance to your specific application. And so that's, again, one of the powers of stack forging is because, we're a toolless process, we're a digital manufacturing process. We can adjust these designs that are, we kind of come up with ahead of time. We can adjust them to meet the specific requirements of any particular customer, right? You need a little bit more flow, a little bit less flow. You have a little bit higher power, you have a little bit more temperature margin, whatever it might mean, we can customize this part to meet the specific needs of your system. Another part I wanted to share was a QSFP cold plate, right? And so this is designed to fit into an existing QSFP connector cage for a single plug, right? So this doesn't require anything other than plumbing to make it work. You don't need to modify the way that your QSFP is built or your cage or anything like this. It's meant to be a drop-in replacement. And again, this is designed and showing in simulation the ability to cool a 50-watt QSFP with a flow rate as low as a tenth of a liter per minute. Right? And so that's awesome. I mean, just being able to bring that kind of cooling performance into a package this small enables so many different system architecture choices, right? And then we're also showing very low pressure drop, right? At a liter per minute in this design, less than the PSI. And as you go down at lower flow rates, that number obviously decreases even more substantially. And this is using a combination of kind of microchannels as well as large scale fluid distribution in order to achieve these very high heat transfer coefficients while keeping pressure drop very low. And so we're excited about components like this because they allow you to bring the benefits of liquid cooling into your system without having to rethink the entire architecture, right? Without having to redesign something like a standard QSFP cage or a standard QSFP implementation. You can just add this cold plate in, add the plumbing into the system, and all of a sudden you're liquid cooled and you're future proofed for the next generation of components. So that was just a couple of examples. We've got a lot more that I would love to talk to you about and that our folks here at Alloy would love to talk to you about. If you're going to be in St. Louis in the middle of November, the 16th to the 21st for SC25, we're going to have a booth there. There's going to be a whole slew of Alloy folks there with parts that we can show you that would be excited to discuss this more and give more details. And yeah, I'm looking forward to the show. I think it's going to be a big one and a good one. It's an exciting time for liquid cooling, and we're looking forward to being out in Missouri and being able to meet with folks and discuss this with them. And with that, I think I can open it up for any questions that folks might have. And yeah, looking forward to discussing more.
Great. Thanks, Bill. So I'm going to go ahead and turn my camera on. And if you want to turn yours on as well so people can see us.
Yep, I got mine on now.
All right. So we have some questions that are coming in. So as a reminder to everyone, just go ahead and pop them in the Q&A. One of them is what kind of thermal interface material options are there for these types of peripherals? And are there any challenges with them?
Yeah, that's a great question. So definitely, the TIM is a critical part of any of these components, and some of them do create some real challenges for the TIM implementation, particularly like the DIMM cooler, right? Being able to have a TIM that effectively provides that thermal path without tearing. There are some options that we're working with now on the market that have protective layers. And it's also something that we're working with some of our partners on for kind of next generation TIMs that give you a better ability to insert and remove these components in the field. So definitely, I think a big challenge in the area and in an area that's aggressively being developed and that we're kind of plugged in with some of our partners to continue to push forward.
Great, thanks. We have another question. Is this based on one phase or two phase systems?
Yeah, so it's a great question. Right now, most of the products that we build and what I showed today are all single phase designs. We do have the ability to do two phase at Alloy, and there's some unique properties of stack forging that I actually think make our process very amenable to two phase cooling. It's a little bit more on the tech roadmap. We see it as a little bit further out in terms of industry adoption and application. So yeah, focused on single phase today, but we do have a two phase roadmap. We'd be happy to discuss with folks in another setting.
Great. Someone else asked, what's the average lead time for prototypes for something like a loop for DIMMs?
Yeah, so it really depends on the specifics of your project and kind of what you're looking for. We typically quote kind of 6 to 8 weeks, but we can move faster than that when the need be. I'll say that's for everything from clean sheet design, simulation, design and testing, and then shipping the prototype, right? Not just the production time. We can typically move much faster than that when we're in kind of a production opportunity where we have, a design settled and things like that.
Great. Okay, let's see here. Um, just a couple more rolling in. I know some people here have some questions like specifically around our stack forging process. I think that if you go to our website, since this webinar we're focused more on peripheral cooling, but if you want to learn more about our actual manufacturing process, as Bill had mentioned, there is a white paper on it that you can get without even filling out a form on our website under resources. And there's also a really great video that explains our process that you can find on our website on the homepage. All right, let's see here. Someone else asked, so if this is a single phase, are there any leak risks?
That's a great question too. And obviously, leaks are something that I think the entire industry is keeping their eyes on and concerned about, right? You don't want to put a component on top of, $5 million of GPUs and risk a leak destroying that component. That being said, our process is actually really much better than what you would see from traditional manufacturing for leaks because we don't have a lot of joints in our products, right? So when we stack forge a part, it comes out as, like I said, a monolithic piece of metal, right? And so there's no brazing joints, there's no glues, there's no areas where we had to join two pieces of metal together. They come out as a single unitary piece of metal. And so once we've leak checked that component, it's very leak tight, and there's not really opportunities or places for like say corrosion to get in and weaken a braze joint and then cause a leak over time. On top of that, we've done pressure testing with our components, and because of the way that we build them and the way that we're able to add in kind of structural rigidity into the component, we're very pressure resistant, right? So we've taken like the kind of that Blackwell cold plate that I showed earlier. We've taken cold plates like that over 2000 psi with no deformation and no leaks. And so our components are actually really very well built for to eliminate leaks from the system and to be highly reliable.
Great. Okay. Um, we'll give folks maybe couple more seconds to type in some questions. But if we didn't get to any of your stack forging questions, go ahead and email us info@alloyenterprises.co, and we're happy to take that conversation offline. All right. Well, with that, I think that this was a very nice, short and sweet webinar, which is great. And oh, this one came in. What alloys are you currently using in these
Yeah,
applications?
another great question. So at Alloy, we use two different materials, or we can make components of two different materials. And so for data centers, typically, and what I was showing there, it's pure copper 110 that we're using. We also have the ability to make components out of aluminum 6061. Personally, I love aluminum. It's an awesome material. It's inexpensive. The strength to weight ratio is incredible. It has great thermal management properties. The galvanic corrosion challenges between that and copper really preclude its use in data centers. And so we have the copper to serve the data center market, but I'm really excited about the potential for aluminum moving forward as a potential material for kind of next generation systems.
Awesome. Well, thanks, Bill. Thanks everyone for attending. Like I said, any questions, if we didn't get to you, go ahead and email us info@alloyenterprises.co. And yeah, we'll send you the recording right after this. All right. Thanks.